Hi there, guys. Well, welcome back again. We're about to work on 5G, and 5G is again working on standard deviation. And what I've mentioned before is that there is a correction to the standard deviation of the sample to make it closer to the standard deviation of the entire population. And this is called Bessel's correction. And that's mostly what we're going to be talking about for this. And in fact, we can do this quite quickly if we just know, I can say it now, we can say that the way in which we do this is to multiply the uncorrected sample variance by the factor n over n minus 1. Okay, there you go, there it is. But we're going to talk it through a little bit, and we're going to try and see if we can make some sense of this. I hope to make a little bit of sense of this. In fact, this goes really quite deep in terms of statistics, and it's really not as much as you need to know, but I'll go through the stuff in the book and I'll add some more kind of proofy type work on the end. Okay, so let's have a look at what the book is saying here. So first of all, the book opens up with an investigation. It says, well, look, we can write the variance like this thing here, at the top. This variance equals the square root of sigma x minus mu all squared divided by n. And likewise, we should be clear on this. You can replace that by x bar. It's allowed to replace that by x bar, but you'd be reducing your population down to the sample. Okay, so that's still valid for x bar, but that would then become the sample standard deviation. So mu can be replaced by x bar. However, if we want to go from one to the next, there's a correction that we need to make, and that's what we'll talk about. But anyway, in this investigation, they just lead your standard deviation at the top formula there to the standard deviation formula where it comes up on point number 8 there, which is essentially what we talked about in the previous exercise. They're saying the sum, in part 8, it's saying the sum of your values squared. If you take the average of those, and then you take away x bar squared, so sigma x over n is x bar, so take away x bar squared and then square root. That's the same a way of doing the variance as the original formula they give there as well. Now that's given in the formula booklet. Again, let's just remind ourselves, the formula booklet from the variance there comes up with two methods. They're using mu, they're not using x bar, and they're using the f there just to say, well, it's possible we have lots of these x1s, xi's. So, let's save ourselves a bit of time by just timesing all these results we get, the difference between xi and mu, and squaring it by f. If we've got it multiple times, let's times that answer by f. So that's like a table version, to be honest, but you can get rid of the f there, it doesn't really matter. We can do it without using a table, essentially. Okay, so that's that. That's a little investigation. And now after that is when they start talking about, so they do an example of that one. I'm not going to do that. We did that last time. And now here it is. It says, you don't have all the data available to you, they're saying, from S of n. Saying you don't have all the data available, and you'll have to estimate the mean and standard deviation of the population from this sample. Okay, in order to make an estimate from for the population mean, you can just use the sample mean. It's an unbiased estimator of the population mean. Okay, now our course doesn't go any further than that. For that, it's just saying, well, listen, X bar is as good as you're going to get for your population mean. We shouldn't add one to it. We shouldn't take one off it. It's likely to be in the center. It's probably not going to be the same as the population mean, but it's the best estimator that we can come up with. However, that's not the same case for the standard deviation. So in terms of the standard deviation, when you're doing your variance, let's just take this thing here, okay, sort of take it through a bit. So normally you would divide by 25 when you're doing this thing here, when you're doing the sum of these residuals squared, if you like, divided by n, and n would be 25 in this case. Now that's what you would normally do for the sample or for the entire population if you have the data for the entire population. So you can still call that sigma squared. Now, if instead we're calculating an estimate for the population standard deviation, we need to divide by one fewer. We need to divide by n minus 1. So, oh, sorry, we're not going to call that sigma anymore. We're going to call this Sn minus 1. Now, some people will call this sigma n minus 1. And I think on the calculator, it calls it Sn minus 1 squared. Okay, so that's still like the square of the standard deviation, but it's just saying we're going to use n minus 1. Now, why are we doing that? Well, kind of short answer is to say, well, actually, when we take into account the entire population, we're expecting our results, there's our sample. We're expecting the spread to be slightly greater when we've got the entire population. Maybe you'll have answers out here, maybe you'll have answers out here, and then you'll have loads and loads in the center. But we're expecting that the population standard deviation will in fact be slightly larger. Okay, and so dividing by n minus 1 means that we're not dividing by something quite as big. And if we divide it by something bigger, if we divide by n, we make the number smaller. Okay, so by dividing by n minus 1, it makes the population standard deviation that little bit larger. Now, it's really difficult to explain why that's the case, but I'll try and explain some of the reasoning for it at the end of this video. Now, before we do that, I'm going to finish off the content before we get to the exercise. And I'm also just going to think, how do we get from your regular variance to this variance here? Let's call it Sn minus 1. How do we get from one to the other? So we definitely, if we have a sample, we definitely know that we can work this out. But then how do you get to this thing over here? Well, of course, you could just, you could just do this calculation here. But if you've got this, and if you've worked this out, then what do you do to it? Well, we need to get rid of the n by timesing by n. And then we need to get a new divisor of n minus 1. So we need to create this extra n minus 1 there. So the connection between these two things is we need to do n over n minus 1 of our regular standard deviation. That would be our regular standard deviation for the sample standard deviation, and to make an approximation, an unbiased estimator of the population standard deviation, then we're going to need to times by this thing here. Now, if you want, you can do that straight away by just doing this. No problem. Okay, because this is using x bar. That's not using mu. Okay, so that's, if it was using mu, we wouldn't have to do this. If we knew what mu was, if we were told what the population mean was, then we wouldn't have to do this at all. But normally we're not told that, and we don't know what the population mean is. So we're going to have to make this conversion. Well, you can just do this straight away. But if you're given this, or if you know this, or if you can work this out, and you want to make that conversion, then you need to times by this correction here. So that's another way of writing down how to get our unbiased estimator once we've already got this. Okay, so like, again, I'm just going to repeat that because these are really kind of subtle points, I think. If you've got your data, then you can just go straight to working out your unbiased estimator by remembering that with the variance you divide by n minus 1. If you've got your data and that's what you want to work towards. But if you've got your data and maybe you've even got your calculation and you want to go to find the standard deviation for the population based on the standard deviation of the sample, Okay, and this is the standard deviation of the sample, just as it would be the standard deviation of the population if you put in mu. Okay, then you would just need to do this correction here. Okay, so that's how you go from one to the next. Okay, now you can see that if you actually wanted, say for example, if you want Sn, you want the standard deviation estimation, then you're going to need to square root this thing instead. So we can do, we've got this variance, you can put in there n-1 and square root that. So square rooting that is going to just take this off here as well. So there's another multiplier if you're just going from the standard deviation, the regular normal standard deviation, to our unbiased estimator. Okay, that's a lot of waffle, okay, but these are quite subtle points, I think. So there we go, there's your formula. And let's just have a look at the formula book. Let's see if they give that correction. Well, it seems to me that like they're not giving that. So you're going to have to remember that correction. So just to explain, I did about another 20 minutes after that, stopping a few times, trying to prove why we have this correction, why we divide by n-1, and not just trying to prove that, but also trying to prove that the population variance is always greater than the sample variance. And after all of that, I thought, I've got to spare you guys. Yeah, this is just incredibly in-depth and incredibly detailed and picky and good, fine. There's a proof that it's always nice to have a proof of these things, but I mean, it just goes into such a level of detail and uses things which are beyond what you know in statistics, that it's really pointless in talking about these things. Now, I'll direct you to things, and I will tell you where to go to look at this Bessel's correction if you're interested. But frankly, it's really kind of university level stuff. So I'm not going to go there now. Okay, I'll spare you. But what I did notice is this. Okay, so this is what they're giving you in the book. They're saying, look, Sn-1 is this formula here, where we've got n-1 rather than n on the bottom. But I'm not really pleased with this formula because really, I think it should say here, the unbiased estimator for the population mean is the same value as the sample mean. Okay, so in other words, this X bar is our unbiased estimator of mu. And I think they would say, look, the expectation of this thing here, what we would expect this thing to be is mu. I don't want to go into that now, because that's not where we are, okay? But I think that they're basically missing X bar there. And so they're saying, well, look, what are we going to put in for mu? Well, we're putting in our unbiased estimator, which is really, I don't like this really, because I think that this should be X bar, because that's our estimator that we're using. Remember, we're only making this change to our standard deviation for the sample to get to this population standard deviation, well, which we can still call sigma if we want to, by the way. But to get to this Sn-1 squared, which is what the calculator is calling it, then we need to we either need to have all of the values in the population, but assuming that we don't, then we need to use X bar in here. And then instead of dividing by n, we need to divide by n-1. Okay, now I've talked about that. This is the formula which they're giving you. And here you need to replace your mu by this X bar. And that gives you your unbiased estimate from your population standard deviation, given that you only have a sample. I think I need to stop there on that. Now let's have a look at, there's a little explanation here about degrees of freedom, and I'll talk about that briefly. But there's an example, of course, and the example here is, it's just doing this longhand. It's just, instead of dividing by n, it's dividing by n minus 1. It's the same as what we did before. It's doing all the x minus x bars squared, all those residuals squared, sum together, and then divide by n minus 1. Okay, so there's that. So I'm not going to go through that one. I'm going to try and deal with this degrees of freedom a little bit, though. And I'm going to point you in the right direction. Now, the thing that you need to go to is Bessel's correction. Okay. And they're saying, well, look, multiply the uncorrected sample variance by this factor, n over n minus 1. Okay, so in other words, let's get rid of the divide by n on the variance by timesing by n, and now let's divide by n minus 1. That's what we've already talked about. Now, the reason why that's happening, and I'll give the short version of this, is that your degrees of freedom have been reduced by 1. And that's because when you look at your residuals, maybe you have 10 residuals there, x1 minus x bar, all the way up to x10 minus x bar. But in all of those 10 calculations, you are depending on x bar. And x bar comes from x1 to x10. So that's what we call our degrees of freedom, because we're basing our calculations on one data point which comes from all the others, then we've lost a degree of freedom there. And you can think about this as saying, well, look, when you add all of those together, you're going to get 0. You can check that out, okay? You can do x1 plus all the way up to x10 and realize that that's our x bar n times over. That's x bar without dividing it by n, okay? So seeing as we have x bar n times over taking away from this, it becomes 0. So that's not normal, right? Because really, we should be taking away, if we want the population mean, we should be taking away the population mean. We should be taking away mu each time. And mu is extremely unlikely to give you the same answer there. Is extremely unlikely to give you the same answer as x bar. So your residuals shouldn't sum to 0. And the consequence of that ultimately is that since the residuals don't sum to 0, you always get, and there's a proof for this, but you always get an answer which is bigger. Now, the proof for that is what I did. I did this, and I'm not actually going to inflict this on you. And that's like, there's a sort of, they look at an example here, and they go through the kind of the working out in this example, and they go through each of your lines and compare it, compare the population variance with your sample variance to show that one is bigger than the other. But that's not a proof. And then I quite liked. I mean, I say like, I like this the second proof of correctness, and this is interesting, or at least potentially interesting. There's a Wikipedia page on this. Some people find it interesting. And there's lots of technical parts to this, and I take my hat off to you if you spend an hour trying to go through this. It's not going to take you that much further with your maths, but there's no such thing as a wasted 15 minutes in maths. Okay, so, but they still, in this definition, they still don't prove why you're dividing by n minus 1. They actually say, look, and by definition, we divide by n minus 1 rather than n. So they're still saying that's because of the degrees of freedom. So, I think there's not a perfect answer to this, and if there is, it's way beyond us. So, that could be frustrating, I know, but I really think that you shouldn't have to listen for much longer. Okay, so there we go. I would direct you to this page here, and it's relatively easy. Probably take you an hour to try and figure out why the population variance is bigger than the sample variance, and that relies on work which is really a little bit beyond where we are anyway. But then why we divide by the n minus 1 is ultimately comes down to the degrees of freedom. It comes from the fact that we've used x bar within our calculations for our residuals, meaning to say that we don't have n independent residuals, we have n minus 1, because they all sum together to equal to 0. Okay, I'm stopping. So thanks for listening, and good luck with the exercise. Okay, the exercise comes up with, four questions there. Next time around is cumulative frequency, and after cumulative frequency, it's like an easy one next time around. And after cumulative frequency, we're dealing with correlation coefficients and regression and implication of causality essentially as well. Okay, guys. Well, thanks for listening, and good luck with the exercise, and hope to see you for the next one.